The diagram shows the graph of the cubic function f, defined for x a real number as f such that x maps onto x cubed minus x squared minus x plus 6. Find the coordinates of the point at which f cuts the y-axis. So we want the coordinates of this point here. A cubic function is some sort of a curve. It often has two turning points. This one would be called a local minimum, and this one is a local maximum. They don't all have turning points, but its shape is a curve. Now, I have written down the function using this shorter notation. You don't have to work with this f such that x maps onto, etc. Just write this as f of x. What's so special about the point where the graph cuts the y-axis? Well, its x value is 0. That's what's special about it. Not only that, but it's a point on the curve, which means that it satisfies this function. So if we put 0 in for x, we will get out the y value. You see, if x is input into this function machine, you could think of it as a machine, and the output is y, the y value of the point that corresponds to the input x value. So if x is our input, then our output is going to be 0 cubed minus 0 squared minus 0 plus 6. All of this works out to plus 6. So the y value of this point is plus 6. It's actually just the constant term here. The constant term of a cubic function is the y-intercept. F has a minimum turning point at 1, 5. Let's look at that. 1, 5. It's roughly here. That's the point on the curve, such that the tangent at that point is a horizontal line, or its slope is 0. That's what's so special about a turning point, whether it's a minimum or a maximum. We want to find the coordinates of the maximum turning point, which is roughly here. You can see the x value is going to be negative. Anyway, let's go through that. At a maximum or a minimum turning point, the slope of the tangent is 0. The tangent is a horizontal line. But we know that the slope of a tangent is the derivative of the function with respect to x. And that derivative must equal 0 if the tangent is a horizontal line. So to find out the x value that gives us a derivative that's 0, we get the derivative. We differentiate x cubed minus x squared minus x plus 6. That gives us 3x squared minus 2x minus 1, and we put this derivative equal to 0. And we solve this equation. We find the values of x that make the derivative equal to 0. Those will be the x values of the two turning points. So let's solve this equation here. Luckily, it actually has factors. The factors of 3x squared are plus 3x by plus 1x. For minus 1, we will write down the factors plus 1 here and minus 1 here. You can check that these factors do indeed work. If you do this multiplication, you will get 3x squared minus 2x minus 1. So luckily, this quadratic has factors. If you don't know how to do factors, you can use the minus b formula, of course. Anyway, to check that these are right, we only need to multiply like this. We get minus 3x plus 1x is indeed the middle term, minus 2x. So these are the factors of the quadratic equation. Of course, if the product of these is 0, the only way that can happen is if either of them is 0. So either we have 3x plus 1 equals 0, from which we get x equals minus a third, or we have the other factor equal to 0, from which we get x equals 1. So these are the x values of the turning points. So x equals minus a third and x equals 1, which we saw already. That was given to us actually. Now we want the coordinates of this turning point here. So by solving f prime of x equals 0, we get the x values of the coordinates. So we want the y value of the coordinates of this point. The x value is minus a third. What's the y value? Well, this point is on the graph of f, so it must satisfy the equation of the graph. So we just get, if x is minus a third, we plug that into this function. That's our input, and our output will be the corresponding y value. So we get f of minus a third. So we plug minus a third in here. So you see we have minus a third cubed. Then we have minus a third squared. Then we have minus x, so we have minus a third. And then we have plus 6. If you work out all of this, you will get plus 6 and 5/27. So we can see the picture here. This point has a y value that's greater than 6, a y value that's greater than the y value of the intercept, as expected. So we have minus a third, comma 6 and 5/27 as the coordinates of the local maximum. The lines K and L are tangents to the curve y equals f of x, and L is parallel to K. The equation of K is 4x minus y plus 9 equals 0. Find the x coordinate of the point at which L is a tangent to the curve. So we want the x coordinate of this point here. Just the x coordinate. Since K and L are parallel, let's look at the slope of K. The slope of K will be the same as the slope of L. So that will give us some information about L. How do we get the slope of K? Well, K has equation 4x minus y plus 9 equals 0. So to find its slope, we rearrange it in the form y equals mx plus c. We make y the subject. So making y the subject, we get y equals plus 4x plus 9. When a line is written in this form, this is the y equals mx plus c form, then the coefficient of x is the slope of the line. So the slope of line K is 4. But L is parallel to K, so the slope of L is also 4. Now, let's consider the equation of L. The equation of any line can be written in the form y equals mx plus c. This is the equation of any straight line. We know the slope m, we know it is 4. So we can write the equation of L as y equals 4x plus c. We don't know what this number c is, we don't have enough information. But knowing the slope is 4, we can at least say that L has this equation. Actually, any line with a slope of 4 has this equation. So any line parallel to L has a slope of 4. So this equation here could stand for any line that's parallel to L. All these lines that I've drawn have slopes of 4. C is actually where they cross the y-axis, but that's not too important here. You know, we just have to work with this unknown C. Now, suppose we want to find the coordinates of this point here. Well, we know that the slope of the tangent to the curve is 4. It's this line here. Slope of tangent to f is 4. Now, as I explained earlier, the slope of a tangent to a function is given by the derivative. And we saw the derivative of this function earlier. It's 3x squared minus 2x minus 1. And this must equal 4, the slope of L. So by solving this equation, we will have the x values of not just this point, but this point here as well. So let's solve this equation. This is a quadratic equation because we have x squared in it. We need to get it into the standard form. That means we have to have 0 on the right hand side. The standard form of a quadratic equation is 0 on one side. So we have 3x squared minus 2x minus 1 minus 4, which is minus 5. Now let's solve this equation here. Let's see if it has factors. The factors of 3x squared are plus 3x by plus 1x. What about the factors of minus 5? Well, we could stick minus 5 here and plus 1 here. Minus 5 by plus 1 gives us minus 5. Will we get minus 2x in the middle? Just do this multiplication. Plus 3x minus 5x does indeed give us minus 2x. So these are the correct factors. We put each factor equal to 0. If we put 3x minus 5 equal to 0, we get x equals 5 thirds. If we put the other factor equal to 0, we get x equals minus 1. So these are the x values of the points where the two lines touch the curve. So this value here must be plus 5 thirds, and this value here is minus 1. This is the one we're interested in. So the answer is 5 thirds. So just to summarize, the slope of a tangent to f at x equals 5 thirds is the derivative of f at 5 thirds, which is 4, which is, the slope of this line is 4 as we saw earlier, same as the slope of line k.